Okay, folks, back here for lesson 4. Today we're talking about inclusive and mutually exclusive events. Now, what we need to do is kind of think about how are simple and these events that I just talked about, inclusive and mutually exclusive, how are they compared? Well, mutually exclusive and inclusive are called compound events. Anytime an event has two or more components to it, it falls into that inclusive or into that compound. A simple event is just a simple thing, like rolling a single die. That's a simple event. Compound events would be like, say I'm randomly pulling a card out of a standard deck of cards, right? Now, if I'm only taking one card, is that simple or compound? It still depends. Depends on what probability we're looking for. What are the outcomes we're looking for? The events are what determines if it's a simple event or a compound event. So let's take a look at some of these examples. Okay, so let's start with, say, the probability of taking one card and it being a head. That is a simple event. There's only a single bitty outcome for it. Let's try something different. Let's say I wanted to do a face card or a diamond. Well, now that's different because face cards and diamonds are two different things completely, but there's an overlap because some face cards are diamonds. Or what if I wanted to do an even number or a red card? Again, there's an overlap there. That's compound. The bottom two are called compound events. The top one is a simple event. Now, what if I'm doing 3 cards? Can I still have simple events if I'm doing 3 cards? Well, yeah. What if all 3 of them are heads? That's a simple event. Now, the question would be is, do I pull all 3 out at once? In which case, we refer to it as being dependent. Or am I pulling a card out, putting it back, pulling a card out, then it's independent events. Independent and dependent events by themselves fall into both sets of these categories. Now, what if I wanted to do, say, all 3 face cards or diamonds? Again, that's a compound event because I have multiple outcomes. And if I had 2 even numbers or a red and 1 diamond or a spade, that is a compound dependent event type deal there. Okay, so let's kind of figure this out a little bit nicer. Simple events typically fall into your single events. Okay. Independent events typically are simple. Dependent events are typically simple. Okay. These two can float across into the other category. Now, compound events have basically really 2 big areas. They're your mutually exclusive events and your inclusive events. So let's find out what these 2 are. Okay, so yeah, we'll just put it right here. Okay, mutually exclusive events. In probability theory, if we have the events E1, E2, E3, all the way up to E to the n, are said to be mutually exclusive if the occurrence of any one of them implies the non-occurrence of the remaining n-1 events. So say I had 12 events, and if I wanted one of those 12 events, the other 11 could not happen. That's mutually exclusive. Okay. And inclusive in probability theorem, again, if we have events, all these here, are said to be inclusive if the occurrence of any one of them implies there is another occurrence of at least one of the remaining. So there's an overlap. So therefore, 2 inclusive events can both occur. So now the way this looks at it real simply is, if I had a simple event, and I made like a Venn diagram, all I have is that spot right there. However many things I want to twist and turn into it, all I have is that one spot. That is simple. Mutually exclusive says, okay, well, I've got this group of numbers over here, and I've got this group of values or items over here. They have no overlap. There's nothing in that middle region. There's nothing there. That's mutually exclusive. Now, inclusive is rather interesting because it has that group. It has the other group. And it's got the overlap. So it's all of the areas when we do inclusive. So an inclusive is that whole combination. You have the whole thing. So the question is, how do we deal with problems that are like this? Well, here's how we deal with it. Okay, So let's start first with if the two things are mutually exclusive events. So if two events A and B are mutually exclusive, then their probability that A or B occurs is the sum of their probabilities. So if I want the probability of A or B, then it's just the probability of whatever the A event is, add the probability of the B event is, and we have it. Now this formula can be added on to however many events you have. Okay, so let's take a look at this. Lisa has 9 rings in her jewelry box. 5 are gold, 4 are silver. And if she randomly selects 3 rings to wear to a party, find each of these probabilities. Okay, so what's the probability of 2 silver or 2 gold rings? Well, we have to figure out how many different things can we have? To remember, probability is the number of events of possible outcomes that you have with what you don't know. So in this case here, it doesn't matter the way she puts the rings out, it's just their combination. So we have a combination of silver. Well, she's got 4 silvers, so that's 4, 2. Well, what's the other ring? Well, the other ring is a gold. And let's see, we have 9 total rings and she's taken 3 of them. So there's our probability for getting just the 2 silver. Now, since you can have 2 silver or 2 gold, you can't have both of those. It is mutually exclusive. So now I do it the other way. I'm taking 2 of the 5 gold rings and 1 of the 4 silver. But notice on the bottom, we still have how many total events do we have? There's our 9, and we're using 3 of those. So we have that value all set out there, and that's how we would get to our answer. Now all we got to do is multiply out those combinations, and we find out that this is 30 out of the 84. And this looks like 40 out of the 84. And I would add those together and get 70 out of 84, which would reduce down to 5/6. So there's a 5/6% chance that she's going to have 2 or the gold or the silver. Okay, so let's take a look at the other one. Probability of at least 2 gold. At least 2 gold. So what does that mean to us? Well, that means she could have 2 golds, which is what this grouping right here was. Oops, this grouping right here was. This was 2 golds. So I'm going to copy that. Okay, so we have the 2 golds right there. But since it said at least 2 golds, she could have more than 2 golds. She could have 3 golds. So what's the probability of, so this would be 2 golds or 3 gold. Okay, so for 3 golds, all I have is the C 5, 3 over the C 9, 3. How many ways can she get all 3 of those rings out? And do I have to do the 4 and 0? No, not really, because there's only one way that's going to come out is that if you don't have any of those. So now if I do this again, this was 40 out of 84. And a combination of 5 given 3 times is 10 out of the 84. That gives me 50 out of the 84. And I could reduce that probability down to 25 40-seconds. So if I have mutually exclusive events, I'm just going to find the probability of each individual event using whatever method is necessary. In this case here, it was combinations work really, really well. And then I add the probabilities together. Okay. If they're inclusive events, therefore there is an overlap. So if 2 events, A and B, are inclusive, then the probability of that A or B occurs is the sum of their probabilities decreased by the probability of both occurring. That's what this last little segment here is. It's talking about what happens if they both occur. That part right there. I want to eliminate that part. The reason for it is I have already did all of A here, and then we've done all of B here. Well, if there's an overlap, I've done both an A and a B and an A and a B in both groups. So I don't want that. And that's why we subtract that off. So here we have a problem for us. There we go. In math club, 7 of the 20 girls are seniors, and 4 of the 14 boys are seniors. What is the probability of randomly selecting a boy or a senior to represent the math club at the statewide math contest? A boy or a senior. So, our probability that we're looking at of a boy or a senior. Okay, so what's the probability of getting a boy? Well, there's 14 boys out of the 34 total students. That's the probability of a boy. Now, I would add to that, what was the probability of getting a senior? Well, I had 7 senior girls, 4 senior boys, that's 11. 11 out of the 34 students. Now, we had a problem here in that we have an overlap. I have senior boys in the group, and I've already used them here as seniors, and I use them here as boys. So I got to subtract off the boy and senior group, which is the 4 out of the 34. What's the probability of it being a boy and a senior? So now, all I got to do is add those together, and I would have our answer. And if I add, say I got 25 on top, it would be 21 out of 34. So the probability of getting a boy or a senior is 21/34. Okay, so that's how we calculate these. Now I've got a few problems here I'd like us to do, or to look at anyway, in which I want you to first think, is it a inclusive or a simple or a mutually exclusive problem? Now, so here's what we've got to start with. I have a die is rolled, okay? What is the probability of rolling a 5 or a number greater than 3? Okay, so it's simple if all I wanted was one event to happen. Here I have 2 possible events. So that means it's going to have to fall into the inclusive or mutually exclusive. So is a 5 or a number greater than 3 inclusive or mutually exclusive? And the answer is they are inclusive, because a 5 is a number greater than 3. So the probability of the 5 or greater than 3 would be, well, what's the probability of getting a 5? Well, there's 1 5 out of the whole 6 on the die. What's the probability of getting a number greater than 3? That would be a 4 or 5 or a 6, so there's 3 out of the 6. But then I got to subtract off how many numbers greater than 3 are 5. Well, that's 1 out of the 6. So if I add this all up, I get 3 out of the 6, I get 1/2. So half of the time I'm going to roll a 5 or a number greater than 3. Now what if I have a card is drawn from a standard deck of cards? We know what that is. What is the probability of drawing an ace or a face card? Well, a face card, according to here, is just a jack, a queen, or a king. So when I look at it, since I want an ace or a face card, that's 2 separate things, so it's not simple. But an ace and a face card don't overlap, so this means it's mutually exclusive. Okay, so now what is the probability of drawing an ace or a face card? Now we can do this 2 different ways, and I want to show you both ways. Okay, one way is we can do it through the combinations. I can do a combination. Well, there's how many aces? There's 4, and I want to draw 1 of them. Okay, out of the whole 52, and I want to draw 1 of them. Okay, and then I would have to add to that face cards. Well, there are 3 face cards in each suit, so there's 12. And then we have to do the whole 1. So when I work these through, then I get 1 out of 13 plus 1 or 3 out of 13 gets me 4 out of 13 as my probability. The other ways to do it is to not use the combinations. Okay, so if I wasn't going to use the combinations, I would have just went, okay, drawing an ace, that's 4 out of the 52 cards. And drawing one of the face cards, there's a 12 out of 52 chance there, which gets me a 16 out of 52 chance overall. And both of those numbers are divisible by 4, and I would end up with 4/13. So you can do it without having to use the combinations. All right, one last problem here. One tile with each letter of the alphabet is placed in a bag, and one is drawn at random. What is the probability of selecting a vowel or a letter from the word equation? Okay, so when I look at this problem, I think to myself, what is the probability of selecting a vowel or a letter from the word equation? Well, the equation has vowels in it, so it automatically tells me that this is inclusive. So that means I need to know, what is the probability of a vowel? What is the probability of equation? What's the probability of a vowel in equation? Okay. So the first question is, in a set of alphabet tiles, how many vowels are there? Well, if we just go with the traditional A, E, I, O, U, and U, that says that there's 5 out of the 26 letters in the bag are a vowel. Well, when I look at the word equation, I have 8 out of the 26 letters are from the word equation. Now, how many vowels are in the word equation? Well, I got an A, an E, an I, O, and a U. I got 5 out of the 26. So when I look at this, because all of the vowels are in the word equation, in essence, I can eliminate both of these when I do this group here. So our answer is 4 out of 13. Now, if I want to go through the whole process, I would have done, well, I would have the 5 out of the 26, add to that the 8 out of the 26, and subtract to that the 5 out of the 26, and I would still end up with 4/13 using the whole formula. But there's, so that's why I say you've got to figure out what do you want to do to work through that. So our probability here is 4 out of 13. So those are your mutually exclusive, inclusive events that you need to watch out for in today's probability assignments.